Okay. Hello, welcome everybody. It is our pleasure to welcome Professor Mukhopadhyay at IMSC for the IMSC Diamond Jubilee Colloquium as a part of our year-long program to celebrate both the completion of 60 years of this institute and 75th year of India's independence. Professor Satya Mukhopadhyay is a professor at the School of Physical Sciences at the Indian Association for the Cultivation of Science, ISCS, Kolkata. He got his PhD from the Harishchandra Research Institute, Allahabad, in 2012. After that, he was a postdoctoral fellow at Kavli IPMU, Japan, and the University of Pittsburgh, USA. And he was my batchmate at HRI as well. Professor Mukhopadhyay is a leading expert in particle physics, and now he is aggressively making his way into cosmology as well, and he is going to talk about that, how to connect particle physics with cosmology. And today he's going to talk about particle cosmology, as I said, and specifically on particle dark matter. So without further ado, I will leave the floor with Satya. Satya, please.
Okay, so thank you, Dheeraj, for the kind introduction and for the invitation to give this IMSC 60 colloquium. It's especially pleasant for me to give this talk because IMSC played an important role in my formative years. I was a student, undergrad student at CMI, and during that time many of our teachers were from math science, and in fact in the third year of our courses, which was totally physics courses, all the classes were also held at math science. So we spent the whole year here. So in that sense, it's very special for me to come back to IMSC and give a talk on this occasion. So as Dheeraj mentioned, today I shall be talking about particle dark matter, and therefore for the purpose of this talk, I shall assume that dark matter is a new particle, and in particular I shall focus on production mechanisms of dark matter in the early universe. So we have learned a number of important lessons from cosmology about particle dark matter. In particular, cosmology constrains some properties of the dark matter phase space distribution function, and of course its total mass density. Based on our current understanding from observations, dark matter interacts with itself and with the standard model particles through gravity only. There are of course upper bounds on the other interaction strengths. And the key property of the phase space distribution function that we have learned is that if dark matter is completely collisionless, then its free streaming length should be less than around 100 kiloparsec. If it is collisional, then the length scale of interest is the corresponding Jeans length. Now models of particle dark matter are many, with their primary role in trying to understand the dark matter density through dynamical processes in the early universe. And that's where the particle physics part comes in order to understand how the density might be generated dynamically in the early universe. Therefore, a very natural starting point in particle dark matter discussion is its production mechanisms in the early universe. Now it's very challenging to study dark matter production in the early universe, primarily because the history of the universe for photon temperatures larger than a mega electron volt is completely unknown. All of us are familiar with this temperature line. We are here today. The current cosmic microwave background temperature is around 2.7 Kelvin. That's around 10 power minus 4 electron volts. And the CMB photons that we are observing today came from an epoch when the last scattering happened, and that's around 0.26 electron volts. That's already in the matter dominated era. The radiation matter equality happened slightly before at a temperature of around an electron volt. Now, before that, it was a radiation-dominated epoch, and the study of Big Bang nucleosynthesis tells us that there must have been a temperature of around a mega electron volt in the early universe. That comes from the computation of the light element abundances and checking those answers with the observations of primordial abundances of light elements. But what happened before this 1 mega electron volt temperature is completely unknown. In fact, we do not also know whether there existed a temperature larger than a mega electron volt. And because of this uncertainty about the early universe, it is very difficult to pinpoint the possible mechanisms that might be behind the generation of dark matter density. Remember that everything that we observe today as relics in the standard model, namely the light elements and the neutrino background, which we have not observed yet but are trying to observe, and the cosmic microwave background, are all coming from physics before a mega electron volt. Now, if an epoch of inflation preceded this radiation dominated era, then the Hubble scale during inflation or the reheat temperature are also unknown. There is an upper bound on the energy density in the inflaton field at the end of the slow roll phase, which is around 10 to the 16 GeV to the 4th. And there is, of course, a lower bound on the reheat temperature, which I just mentioned, which is around a mega electron volt. But beyond this, nothing is known about the inflationary physics or the physics of reheating. So this large amount of uncertainty, therefore, leaves us with a very broad range of possibilities about the mechanisms that could have generated the dark matter density that we observe today. Different possibilities, of course, have varying degrees of testability, and we shall only discuss a few of them today. Now, in choosing specific examples to be discussed today, we shall restrict to very minimal scenarios. And by minimal, I mean scenarios with the least number of new particles and least number of free parameters. And some of these scenarios may also have other motivations in particle physics, but that's not the angle from which we'll be coming to. Now, if I have to summarize the zeroth order particle dark matter cosmology in one slide, that will be this. There is an initial dark matter phase space distribution function, which is given by some mechanism that is unknown to us. Once this initial dark matter phase space distribution function is given, a natural question to ask will be whether dark matter undergoes any significant scatterings. If the answer to that question is no, then the next question to ask will be whether dark matter undergoes any significant amount of free streaming. If the answer to that is also no, we'll end up in this collisionless cold dark matter paradigm, which is a C of lambda CDM. In this case, of course, the density is determined by the initial conditions which set this initial distribution function. If, on the other hand, dark matter undergoes significant free streaming, then broadly we can categorize into two different classes. If the free streaming is too large, then the largest structures form first, right? And from there, by fragmentation, the smaller structures form. So that's a top-down scenario for structure formation, which is in conflict with observations, because we have seen galaxies as far as at redshift 10, but we don't see large structures at those high redshift. So we know that the structure formation happened bottom up. The smallest structures form first, and then through coalescence, the larger structures form. Hot dark matter, on the other hand, would predict a scenario of top-down structure formation. So standard model neutrinos, for example, if they could provide the total density, would fall into this hot dark matter category. Right? That's in conflict with observations. Warm dark matter, on the other hand, may have some amount of free streaming up to this 100 kiloparsec that I mentioned, and therefore would be different from collisionless CDM in that aspect. Nevertheless, since both these categories also do not undergo any significant scatterings, it is again the initial phase space distribution function that determines the density today. so we fall in the same box. If on the other hand, dark matter does undergo significant scatterings, then the question to ask would be whether it scatters with a standard model bath. If the answer is no, then we only have dark matter self-scatterings, which may or may not thermalize. If the self-scatterings don't thermalize, again we fall in the same box of initial conditions. If they do thermalize, then there will be a dark matter temperature, which is now different from the standard model temperature in general. Finally, if it does significantly scatter with the standard model bath, we'll end up with the simplest possibility of all of these, which is dark matter thermalizes with the standard model. It is the simplest because we have one less free parameter to deal with. If thermalization occurs, which is in these two cases, then as we know, the temperature and the chemical potential will describe the system completely. However, even if thermalization occurs, one needs inelastic reactions which change the dark matter number in order to dynamically generate the density. Only elastic reactions don't change number, right? So if only elastic scatterings are present, then also the density is just given by the initial conditions. One needs number changing inelastic reactions to have a dynamical mechanism to generate the density. What are the examples of such minimal inelastic reactions? A very well known one will be two dark matter particle scattering to give two standard model particles. A little less known but equally simple would be two dark matter particles going to a standard model and another dark matter particle. That's also another simple topology of 2 to 2. If on the other hand, dark matter does not significantly scatter with the standard model, then the minimal number changing topology will be 3 dark matter going to 2 dark matter, right? Because if there is only one species present, then to change the number through inelastic scatterings, 3 initial particles should go to 2 initial particles. That's the minimal possibility.
In these cases, the chemical potential should be 0.
In this case, the chemical potential is 0.
But then the standard model for the dark matter, it assumes that there is some coupling between the dark matter and standard model.
Right. So the first 2 examples are inelastic reactions in this category, and the third one is an inelastic reaction in this category. It's okay? Yeah. All right. So in what follows, we shall then pick up examples from all these 3 scenarios that can happen. And this is a logically complete set, right? You will either fall in this scenario or this scenario or this scenario. And we'll pick up examples from each and see what happens. So let's start with the simplest one, in which dark matter thermalizes with a standard model bath. So the temperature of dark matter is same as the temperature of the standard model. I shall discuss 2 examples, and in my view, the simplest example in this category is that dark matter is the neutral component of a multiplet of the standard model electroweak gauge group, SU2L. Why is this the simplest? Because once you fix a dark matter spin and representation, there is only one free parameter in this scenario, and that's the dark matter mass. Right? Because the coupling is already fixed by this SU2 gauge interaction. And the mass is also then fixed if this single species saturates the observed density. So this is a scenario where everything is completely known. Now, often popular examples in this category are Majorana fermion dark matters, which are multiplets of SU2. And if they are Majorana fermions, it turns out that the most popular probe of dark matter interactions with standard model, which is dark matter scattering with nuclei in underground laboratories, the spin independent scattering rate, which is enhanced by the coherence effect, is suppressed. And the lowest order cross section comes from loop induced processes, and one generically needs multi-ton scale detectors to detect such spin independent interactions. And therefore, indirect detection becomes a very important probe in these cases. Among the indirect detection probes, the most important is diffuse gamma ray searches from annihilations of dark matter to weak boson pairs. in the center of our galaxy or in dwarf galaxies. One can also have gamma ray lines, which are less background prone signals, but the signal also is suppressed because gamma ray lines come from loop induced processes. Colliders are also important probes for such scenarios, and there is a very interesting signal which is a disappearing charge track search. What happens is, because dark matter now belongs to a multiplet of SU2, so there is a charge partner of the neutral dark matter, and you can produce that charge particle at colliders, and the mass splitting between the charged and the neutral component is loop induced. It's just like charged pion and neutral pion mass splitting, so that's a very small mass splitting, giving rise to a very small decay width. Therefore, once these charge partners are produced in colliders, they travel some distance before they decay to invisible particles. So this delayed decay leads to a disappearing charge track signal, which is very striking and can be probed in colliders. So let's look at the details of two very popular examples of this electroweak dark matter. One is a SU2 triplet Majorana fermion. For those of you who know about SUSY dark matter, this is the typical example of WINO, or SU2 doublet fermion, which is a Higgsino. If the single species saturates the total dark matter density, then the mass of the WINO turns out to be 3 TeV. As I said in the previous slide, it is uniquely predicted, right? For Higgsino, it's around 1 TeV. Naturally, because the interaction strength is smaller, a larger number density is left out, and so the mass that you require to saturate the density is also smaller. Now this loop induced spin independent detection cross section for WINOs is around 10 power minus 47 centimeter square, which requires a multi-ton scale experiment to detect it, and such experiments are underway. So if we are lucky, we can detect such particles soon. For Higgsino's, it turns out that there are cancellations even in the loop level, and the cross section is suppressed by further 2 orders of magnitude. So it's around 10 power minus 49 centimeter square, which is below the neutrino floor. And by neutrino floor here I mean that the neutrinos that are coming, for example, from the sun also become a background to dark matter searches, because they can also collide with nuclei and give a signal. As far as indirect detection is concerned, the most promising probe is looking at dwarf spheroidal galaxies, which are very dark matter rich systems. They have a very high mass to light ratio. So the Fermi-Light satellite is looking at those dwarf spheroidals and looking for gamma rays coming from there. The current bound, if it saturates the total density, is around 400 GeV for the WINO case and around 350 GeV for the Higgsino case, which is much smaller than the thermal target. There is some discussion about the 14-year Fermi continuum gamma ray data giving a hint precisely at around 1 TeV mass particle in this channel, but that's still under discussion. As far as collider probes are concerned, the LHC, which is this 14 TeV row, falls short. As you can see, the disappearing charge track search can probe only up to 900 GeV of WINO mass, but our target is around 3 tera electron volt. For Higgsino, the LHC reach is further smaller to around 300 GeV. So in order to probe these scenarios in colliders, you need higher energy machines, probably a 100 TeV collider. But nevertheless, what this slide should show you is that this is a scenario which is completely testable by one or the other probe. The next simplest scenario, where dark matter does thermalize with the standard model, is that it's a singlet scalar with a renormalizable coupling to the Higgs field. Now the number of free parameters is 2 instead of 1, the coupling to the Higgs and the mass of the dark matter. Previously the coupling was fixed by gauge coupling. Now that is also unknown. But nevertheless, since it now couples at the renormalizable level to the Higgs boson, it will give a strong signal in dark matter nucleon scattering. So that becomes the strongest probe of this. Indirect detection is weaker compared to that. Colliders are also possible probes, especially if the mass of this particle is less than half the Higgs mass, then there is a signal in the invisible Higgs search. Otherwise you have to go to off-shell Higgs. what is the situation now? The current base limits come from this xenon 1-ton experiment for direct search, and that excludes the thermal dark matter mass of around 1 TeV for this scenario. Beyond 1 TeV, it is still allowed. Now, as you can see, for higher and higher masses, to saturate the observed density, I need higher and higher couplings. And soon the computation will become non-perturbative, right? So the perturbative computation will fail. And therefore, a natural question to ask would be, how high can the mass of thermal dark matter be in general? And the answer here comes from the unitarity of the S matrix. The unitarity of the S matrix implies the optical theorem, which all of us have studied in quantum mechanics. It relates the imaginary part of the amplitude of scattering from a state alpha to the same state alpha, where alpha is a 2-particle initial state, to the total cross section of going from alpha to an arbitrary final state beta. That's the optical theorem. Now it can be shown that this optical theorem implies a general upper bound on the total inelastic scattering cross section from a given initial state, and that bound is given by this. This sum is over the orbital angular momentum of the 2 initial state particles. So this is completely general, model independent, and non-perturbative statement. So this equation is the key to determining how high can the mass of thermal dark matter be. Because given the highest inelastic cross section, I can compute the maximum reaction rate for an arbitrary, let's say 2K process for a 2-body initial state. And this maximum reaction rate in turn will imply the minimum surviving number density of dark matter, right? If the reaction rate is maximum, the dark matter will remain in the thermal bath for the longest, and if it follows an equilibrium distribution, its number will keep reducing. So the number that survives will be minimum. Now if that minimum number saturates the observed density, that will give you the maximum mass, right? So that decides how high can the mass of thermal dark matter be. And for these processes where the initial state is a 2-body initial state, the answer for S-wave annihilations is around 130 TeV. So that's the maximum mass of thermal dark matter if it primarily undergoes S-wave annihilation, and the annihilation is of 2-2 type. Now I told you that if dark matter does not talk to the standard model, then the minimal number changing process within the dark sector is a 3-2 process and not a 2-2 process anymore. So we would like to know the same bound now in the case of a 3-2 process or an arbitrary K-2 process, so to say. Now if one goes through the derivation of this unitarity upper bound on the inelastic scattering cross section, there is a step in which you have to go from the usual momentum basis to the angular momentum basis of the initial state particles. That's easy and known for a 2-particle initial state, but for higher particle initial state, going from the momentum basis to the angular momentum basis is rather complicated. So what we could show in this paper is that in thermal equilibrium, I don't need to first determine the maximum reaction rate for a K-2 process, but rather rely on the maximum reaction rate for a 2K process and infer the maximum rate for a K-2 process just by using detailed balance, right? Because in thermal equilibrium, detailed balance relates these 2 rates. And this is the answer for the maximum reaction rate for a K-2 process, which I can now apply for the case of interest, for example, where the dominant annihilation channel is a 3-2 process. And this is the maximum inelastic cross section for that. Now if you plug that in, the maximum mass for dark matter now drastically reduces. It's around a 1 GeV. So that's a very important lesson, that if the dominant inelastic process is within the dark matter sector, so it doesn't talk to standard model, then the maximum mass for a thermal dark matter in this case is 1 GeV if it primarily undergoes S-wave annihilation. Knowing the maximum mass is useful because this gives us a target when we are trying to probe these scenarios. Now you can understand, if you go on increasing the number of particles in the initial state, this maximum mass will just keep going down, simply because the maximum cross section is going down. Now so far, even while considering thermal scenarios, I have only talked about the temperature. But of course I mentioned in the beginning that if thermalization happens, then it's the temperature and the chemical potential which describe the system completely. So what about the chemical potential of the dark matter? Now before going to the chemical potential of the dark matter, let us look at the chemical potential of the standard model particles that we know of. The baryons and the electrons do have a small chemical potential. We know that there is a baryon-antibaryon asymmetry of the order of 10 power minus 9 in the universe, which leads to a small chemical potential for baryons, around 10 power minus 4 in the units of the baryon mass. For neutrinos, the chemical potential is only weakly constrained by Big Bang nucleosynthesis. It should be less than around 10 power minus 2 times an MeV. So therefore, if dark matter had a thermal equilibrium history, then in general, it can also have a non-zero chemical potential, just like neutrinos or baryons. A priori, we do not know. Now what changes if it does have a chemical potential? Of course, if there is a non-zero chemical potential, then there is a dark matter particle and an antiparticle, right? If it's self-conjugate, of course the chemical potential is 0. And in determining the total dark matter density is the sum of the two densities which is now relevant. And as you can easily compute, the sum of the dark matter and anti-dark matter density is now modified by a factor of this cosine hyperbolic dark matter chemical potential divided by the freeze-out temperature. So for the same freeze-out temperature, the chemical potential enhances the net number of particles that are left behind. So that's the role of the chemical potential. Now if there is a chemical potential, there must be a particle-antiparticle asymmetry. That's the general result. Now once an asymmetry generation process freezes out, then the difference between the dark matter and anti-dark matter number also freezes out, right? Okay, I think the pointer probably stopped working. But anyhow, you can see this equation, y chi minus y chi dagger is C. So that freezes out, right? So after that remains a constant. There can of course be subsequent pair annihilations, right, which remove the symmetric component. And the observed density of dark matter now is related both to this difference in the yields and the annihilation rate. This is exactly same as for baryons. Okay. So if you take the small c limit of this equation and then take c goes to 0, you will recover the fact that the density is inversely proportional to the annihilation rate, which is the standard result for 2 to 2 dark matter annihilating to standard models. Now for the case of complete asymmetry, this annihilation rate now becomes irrelevant, again as for baryons. And you can see that if the asymmetry in the dark matter sector is of the same order as the baryon asymmetry, then the mass of the dark matter is predicted to be around 5 GeV. This is also easy to understand because when either only the dark or the anti-dark matter survives, it is the asymmetry that decides the density. And if the asymmetries are comparable, then the densities of baryons and dark matter are also comparable. And since the total dark matter density is around 5 times the baryon density, so the mass of the dark matter has to be around 5 GeV, which is 5 times the proton mass. Now, okay, sorry. So as I mentioned, just like for baryons, one usually needs 2 different processes in such scenarios. One process that generates the asymmetry and a second process that eliminates the symmetric part. What we could show in this paper is that if you have a process like this, which I mentioned before, where 2 dark matter particles annihilate to an anti-dark matter and a standard model-like state, this is so-called a semi-annihilation process, then only one process can do both the jobs. That is because in this process there is a dark matter number violation, so you can generate an asymmetry, as you can see, that if you assign a dark matter number of -1 to the antiparticle and dark matter number 1 to the particle, then the net change in dark matter number is -3 in this process. And there is also removal of one component, because in every reaction the total number of dark plus anti-dark matter reduces by 1 unit. So one process can do both the jobs. And we could see that for perturbative couplings, this process can also generate nearly maximal asymmetry. Now let's move to the second scenario. So those are the brief remarks on the chemical potential. In the second scenario, dark matter doesn't talk to the standard model, so it self-thermalizes. Now if it's a scalar particle, then it is very natural to have self-scatterings and annihilations, right? And with no significant scatterings to the standard model bath, of course the question would be, how does its initial density come about? It can come about from reheating, for example. So post reheating, if the inflaton is much heavier compared to the reheat temperature, then dark matter will undergo only self interactions, right? Which may lead to internal thermalization and its own temperature. So in such cases, the dark matter phase space density evolves by this kinetic equation, right? Where the left hand side is a differential operator and the right hand side is an integral. So this is in general an integral differential equation that determines the properties of the dark matter phase space distribution. Now the way we proceed in such cases is to take moments of that integral differential equation. So if you take the 0th moment of this kinetic equation at 0th order in an FRW background, then you obtain the equation for the evolution of the dark matter number density. If you take the second moment, so multiply both sides of this equation by p square by 3e and integrate, then you obtain an equation for the evolution of the dark matter temperature. So in general, you have to solve this coupled system of equations to know how the dark matter number and the temperature evolve. Of course, in this case, the initial condition of the dark matter temperature is unknown, right? Which may be determined by the reheating dynamics. So a simple example for such a scenario would be simply a singlet scalar, which naturally has a cubic and a quartic self interaction. Now as you can see, if there is a cubic and a quartic self interactions, then not only we will have elastic scatterings through the chi to the 4th term, you will also have 3 to 2 processes involving both these vertices with lots of possible Feynman diagrams. As Dheeraj mentioned, if such 3 to 2 processes happen, then the chemical potential is 0 when these processes are in equilibrium, right? So only the temperature describes the system. Now a very interesting thing happens in this case, and that is that the temperature evolution of dark matter when this 3 to 2 process is active is very non-standard. Now usually you know that the temperature in an expanding universe of a relativistic particle falls as 1 over the scale factor. That is this black line. For a non-relativistic particle, the temperature falls as 1 over the scale factor squared. However, when these 3 to 2 processes are active, the temperature of the dark matter species only falls logarithmically with the scale factor, which is much slower. The primary reason for this is that when such a 3 to 2 process happens, of course the expansion of the universe is trying to reduce the temperature because it's stretching each momentum mode. However, when these reactions are happening with non-relativistic dark matter particles, 3 dark matter particles are annihilating to produce 2 dark matter particles. So the mass of one of the dark matter particles is being converted to the energy of the other 2 dark matter particles, right? Pumping up the temperature slightly. So it reduces, of course, due to the expansion, but nevertheless it reduces much slower than both relativistic and non-relativistic expectations. Of course, after this process decouples, it will fall as 1 over a square, which is characteristic of non-relativistic particles. Now this non-standard temperature evolution plays a very important role in the cosmology of such dark matter particles. So we can ask two questions, right? Because the temperature is unknown, we need to know what the upper bound on the temperature is and what the lower bound on the temperature is. Now there is a very strong upper bound on the dark matter temperature from the study of CMB anisotropies, right? They predict that the temperature of dark matter at the time of last scattering should be around 10 power minus 5 times the mass of the dark matter. So if the dark matter is very light as let's say 10 electron volts here, then the temperature has to be 1,000 times smaller than the standard model temperature. Otherwise, it will mess up with the CMB anisotropies. Of course, as the mass increases, the upper bound on the temperature from CMB also reduces. But nevertheless, it has to be lower than the standard model temperature. That's for sure. BBN will also constrain this scenario if these dark matter particles are relativistic at the BBN epoch, simply because it will contribute to the effective number of relativistic degrees of freedom. But the CMB constraint turns out to be stronger in most cases. Now what about the lower bound, right? The lower bound comes from the fact that if I keep reducing the dark matter temperature too much, right, its number density will go down very fast. And that will reduce the annihilation rate of these 3-2 processes drastically. If that happens, then these 3-2 processes will never be in equilibrium. And the whole scenario will fall apart. So the dark matter density will no longer be generated dynamically by the freeze out of the 3-2 processes. So that sets a lower bound on the dark matter temperature, which is rather weak, as you can see from this region. So now let me move on to the third possibility, in which the dark matter phase space distribution does not thermalize. Now there are a large number of possible examples here. Dark matter can mix with or can have small couplings to standard model particles, or it can be produced in reheating. The examples in category 1, where it can have a mixing with standard model particles, for example, is that dark matter is a sterile neutrino, and it mixes with ordinary neutrinos through this renormalizable term in the Lagrangian. And through that small mixing, you can generate a non-thermal density of dark matter particles. The second possibility is that dark matter is produced at reheating, and then its distribution depends on the conditions for reheating, the reheat temperature and the duration for reheating and the inflaton mass, which are all unknown. So in what follows, I shall consider a very simple scenario in which at the end of the slow roll phase of inflation, the inflaton field undergoes a damped oscillation around the minimum of the potential, and I shall assume that the minimum of the potential can be approximated by a quadratic form. If that can be done, then this is equivalent to a field theory of massive spin zero particles with negligible velocities. So it's only the inflaton zero modes that are relevant. So in this case, for example, a simple Lagrangian to describe the system will be the inflaton phi couples to the Higgs through this renormalizable interaction, and that's how it reheats to the standard model sector. And it couples, for example, to a singlet fermionic dark matter particle through another renormalizable interaction. So through the decay of the inflaton zero mode, the initial dark matter phase space distribution will be determined. Now this particular shape of the initial phase space distribution function, which just follows from this equation, is easy to understand. At the beginning of the reheating phase, whichever particles are produced, their momentum is maximally redshifted at the end of reheating. So this is a distribution function plotted at the time of end of reheating. However, and so these are the suppressed modes. However, the maximum number of particles are anyway produced towards the end of the reheating, simply because of the exponential decay factor. So that gives rise to the shape of the distribution function at the end of reheating. Now what is the typical coupling that you need to produce the observed density? For a mass of dark matter around a 10 kiloelectron volt, which is a typical example that I have taken here, and an inflaton mass of 5 TeV, the coupling turns out to be around 10 power minus 8 or minus 9. It doesn't change much if you change these parameters. And this is good because if the coupling necessary was larger, through loop effects, that could have destabilized the inflaton potential and disturb the slow roll conditions, which should not happen. Now, an interesting question to ask in such a case is that now, since the inflaton necessarily couples to both the standard model and the dark matter fields, can inflaton mediated scatterings become important in dark matter cosmology? Of course, it will become important only if the inflaton is not too heavy, right? Otherwise, these scatterings would have very negligible rates. So, in the example that I considered, right, the scatterings are, for example, 2 dark matter particles scattering to produce 2 dark matter particles. So, that's an elastic scattering mediated by the inflaton, or a dark matter and a standard model particle, the Higgs boson, scattering to another dark matter and the standard model particle, which is another elastic scattering reaction, or an inelastic scattering reaction where a pair of dark matter particle annihilate to a pair of Higgs boson. All these processes can happen through the inflaton exchange. And these scattering reactions, they need to be included to solve this integral differential kinetic equation that I showed you earlier, to see the evolution of the distribution function. So, just to take an example, this green dot dashed region is the distribution function that I showed in the previous slide, the same one at the end of reheating. And if I did not include these scattering effects, then each momentum mode will simply get redshifted. And so, at a later epoch, for example, here I am showing the distribution at a temperature of around a mega electron volt, it will simply be, it's the same shape, but all momentum modes redshifted. However, on including the effects of scatterings, we can see that lower and lower momentum modes start to get populated, which is what we expect. Because if you keep the scattering reactions going on for sufficiently long time, eventually the system will thermalize. And if the thermalize, that produces this black curve, which is the Fermi-Dirac distribution. But of course, we are in an expanding universe. So, at some point, these scattering reactions decoupled. And in this example that is being shown here, thermalization never happens. However, because the lower momentum modes are getting populated, the average velocity dispersion of dark matter can get drastically modified. So, in this case, for example, if you don't include this effect of inflaton mediated scatterings and compute the free streaming length of such dark matter, it comes out to be around 0.07 megaparsec. But on including the scatterings, it can get reduced by a factor of 40, which is a very large factor, and which can decide whether this scenario is allowed or disallowed by current measurements even. So, indeed, inflaton mediated scatterings can become relevant as long as the inflaton is not too heavy. Let me skip this slide and come to the summary. So, we saw 3 broad categories for dark matter production in the early universe. The simplest possibility was that it thermalizes the standard model. And we saw that the simple scenarios in this case are highly predictive, widely tested, and very much viable at present. Right? I mean, very often we see in the current literature people arguing or saying that such simple dark matter models, which were thought before, are kind of ruled out now, and we should move to more and more complicated models, but that is untrue. Right? I showed you 2 very, very simple examples, which, even though are widely tested, are totally allowed at the moment. The second scenario that we considered is when the thermalization is only internal. Dark matter doesn't talk to the standard model. Here, the initial dark matter temperature is constrained by cosmology. There are strong upper bounds from the cosmic microwave background, but only weak lower bounds. And in the case when there is no thermalization, of course, the density depends on the initial conditions, possibly of an inflationary epoch for which we don't yet have a very detailed probe. So, moving forward, given this large number of possibilities, how are we to make progress? One primary question, in my view, in dark matter astrophysics or cosmology is whether there is any evidence to go beyond this cold collisionless paradigm. For example, a specific question to ask would be whether there is a small scale cutoff in the matter power spectrum. If indeed one finds that there is a small scale cutoff in the matter power spectrum, that would imply a lot about the dark matter phase space density and its properties. And finally, whether we can learn any lessons from astrophysics at the galactic scale, which is of course very complicated because of the gas dynamics involved. The cosmology is of course much simpler. But nevertheless, we should also look at the galactic astrophysics and try to see if anything important can be deduced about dark matter properties from them. So I'd like to end there, and thank you for your attention.
Thanks, Satya, for giving this brilliant overview of to explain that why this merger of particle physics and cosmology is important. And now the floor is open for questions. If you have any questions, please.
So there were some cutoffs that you put on the dark matter masses depending on whether related to 3 to 2 processes, 4 to 2 processes. Mm-hmm. Can you discuss that with the ruled out reason from the xenon 1-ton experiment? So is that in okay. What are the possible scenarios from here that are being,
okay. So this is the maximum mass that is possible, right? Let's just take the 2 to 2 case, okay? So maximum mass is 130 TeV, right? And this is a non-perturbative statement. It is a model independent statement, right? So whatever model it may be, if the dark matter density is produced thermally, then its maximum mass is 130 TeV, right? Now, can xenon 1-ton probe this mass? That's your question, right? Now, of course it can probe. But what kind of couplings it probes at 130 TeV is the relevant question, right? And it turns out that the couplings that it would be able to probe at 130 TeV would violate this unitarity, right, on upper bound on the cross sections. So naturally, particles as heavy as this, if xenon can probe, then their densities have to be produced non-thermally. Right? And for the other ones, right, where 3 to 2 and other reactions are the relevant ones, here, as I said, dark matter doesn't even talk to the standard model. Right? So then xenon, etc. are not probes. Right? But for non-thermal dark matter, for example, I want to point out that experiments like xenon are sensitive to dark matter masses even as high as 10 to the 6 GeV. Right? If the coupling is just of the same strength as neutrino coupling to Z bosons, right? So those are all ruled out. But with those couplings, 10 to the 6 GeV mass particle will be overabundant, right? And so that has to be non-thermal.
Any other questions?
So here, in all of these, you assume that the dark matter is made of one single component, right?
Correct.
So suppose we have multiple components of dark matter. So then can you put in like more bounds or stringent bounds?
No, it will be more weaker, right? I mean, even with one component, you see the number of possibilities is so large, and we are trying to at least categorize, right? If you have more, right? But I want to make a remark here, right? I mean, let's look at the baryon sector, right? I mean, it is true that the standard model has many particles, but what is left is mostly a bunch of protons, right? And some electrons to go with it. So it is only these protons and some photons which are not much density today. So it's only the protons that make the baryon density today. It's one particle. Even if the standard model has lots of particles, right? The surviving particle in the standard model sector is basically the protons. And the properties of the proton density are determined simply by this physics, right? So it's just two numbers, this y chi minus y chi dagger in the proton sector and this annihilation rate between protons and antiproton, which is so large that it is irrelevant and you are left with this scenario. So again, in the baryon sector also, right? I mean, in the standard model sector also, even if you have a very large number of particles, right? In the end, the density that we see is determined by one particle, and as dynamics as simple as this, right? So the same can happen in the dark sector.
No, but for there was this, had at some point some equilibration, right? And then the proton was the lowest mass baryon.
Right.
There may be multiple towered of states, but they may go out of equilibrium or something would have happened, or even in equilibrium, those contributions are very less in thermodynamics.
Right. If you have multiple stable particles,
yeah,
of course. And if there is a tower, so one is heavier than the other, right? And the heavier particles, you're saying, might have gone out of equilibrium.
In principle, if there is a QCT phase transition, then all possible baryons were there in the system.
Right.
But at some point of time, the universe cooled down.
Right.
And then the temperature comes out to be about the mass of proton. Then all of those, the temperature comes out to be much cooler, much less than the mass of the baryon. Then the lowest mass baryon contributes to the thermodynamics maximally.
So the same can happen here also. Right?
Okay.
Yeah. And anyhow, I mean, as I said, I mean, even with one particle, the number of possibilities is very large, right? And it is hard to categorize, as you can see.
Yeah, but if your dark matter mass is much higher,
right,
then it is a good mechanism. But if your dark matter mass is, of course, near the mass of proton or less, then there will be a problem. Then the multi-component thing will be maybe a possibility.
No, but you don't need, right? I mean, as I said, so for example, if there is an asymmetry, right, a 5 GeV dark matter is enough, right, to do the job. Or if there is only internal thermalization, right? A 1 GeV particle can do the job. So even with a light particle, there is no problem if there is only one species. Right? So a simple 3-to-2 reaction within the dark sector can set the density very easily, and the maximum mass is only 1 GeV here. So even for light particles, I don't see any necessity for requiring multiple number of states, right?
No, it's not, it doesn't require, but if it has many, then what will happen?
Then the things will be more complicated, right? I mean, as I said in the beginning, I'll only discuss simple scenarios with the least number of free particles.
Of course, this mass range is fine, but this lowest mass range, that is a bit...
But here?
Yeah.
Why is it a problem?
Not a problem, but then there may be possibilities that multiple dark matter candidates may be there in the thermal bath, and all of them may be important.
Sure. I mean, so you know, what will happen is you probably need somewhat smaller or larger coupling depending on how many particles you have. But then the things become more complicated, right? I mean, even with this simple case, right, we are struggling, right? So I think it's yeah.
Thank you.
So with these heavier dark matter particles, so like some GeV dark matter particles, so do they also have some decay channels? And if they have some decay channels, do they also contribute to, I mean, modification of these predictions, or do they lead to some new models which will give some newer predictions about the dark matter?
Well, of course. So if it decays, right, we have to be careful, right? The decay lifetime should be very large, right? It has to be dark matter, right? Now, if the decay lifetime is very large, right, then it should not play a major role in cosmology, right? It should be at least as large as the age of the universe, but actually given current constraints of dark matter decay to standard model final state, it should be much higher than the age of the universe. So if it decays so slowly, right, then it probably doesn't have a much role in cosmology, unless a small fraction of it decays during BBN or CMB. Right? If it decays even a small fraction during BBN and CMB, right, we know the physics of BBN and CMB so well, and if it disturbs, right, if it injects electromagnetic or hadronic energy into the bath, in the standard model bath, then it can disturb those processes. And so then the decay rate will be constrained by cosmology. Right?
Thank you.
Are there any other questions? No? So if not, let's thank Satya again for this brilliant talk.